Okay, so we have the general title of this section called weighted average word problems, but to be honest, what you're going to find with several of these is making a chart with language that is going to be more understandable to you is going to be better than any generic thing I can give you. So there's going to be some generalities I can give along the way, but just understanding where the pieces are coming from is going to make this easier for some of you to be able to do. So, okay, enough of that gibberish. Let's go to this. Every year, the junior and senior classes at Hillcrest High School build a house for the community. If it takes the senior class 24 days to complete it, and they work with the junior class, and it takes 18, how long would it take the juniors if they worked alone? You're like, wait, we did this yesterday. We did something similar yesterday. The change today is, and this is something you've got to watch for, is, so I know how long it takes the seniors. Here's the twist today. Work with the junior class. This is the together number, not the juniors on their own. What we're looking for is, if the juniors were working alone, how long would it take them? This is going to get set up a little bit differently than we did it yesterday. So, I'm still going to make charts because I like to kind of visually organize things as I go. So, we know that how fast you work, the rate, times the time that you spend at that job is going to equal the part of the job that you complete. Okay? I mean, it's as simple, if you wanted to look at it this way, as, hey, you know, if I knew I could make 4 cakes in an hour, I don't even know if that's legit or not, and I worked for 6 hours, how many cakes could I make? I could make 24. I'm multiplying them together. I wish it was that simple. Not quite. So here, I'm even going to do one more little label. I'm going to do seniors and juniors here, just to make sure I know everything that I'm putting everywhere as I plug these numbers in. Okay, so what do I know? I know that it would take the senior class 24 days. Now, I'm not going to put 24 as my rate. Just like we talked about yesterday, there's one job, one house that I'm trying to complete. So each day, the seniors complete 1/24 of that. Now, here's the good news. Time-wise, for this job, if they're working with the juniors, it's going to take 18 days. So the time is 18 days for both because they're working on the same house. So I want to make it clear that that is going to be days. So we'll put that in here. But this becomes the interesting part. You're like, well, what about the juniors? We don't know their rate. It's a mystery. So since the juniors are a mystery, it's 1 over x. I mean, you could use 1 over t, but it doesn't matter. It's a variable. And so if you multiply the values together, because it's rate times time, 1/24 times 18 would be 18 over 24, or 3/4 if I reduce that. So the seniors could do it a little bit longer, 3/4 of the job in that much time. The juniors, if I multiply across, is 18 over x. So just like when we were talking about yesterday, if you take the senior part of the job plus the junior part of the job, we finish 1 complete house. That's the tricky part, okay? We're done with the tricky part. Now it's time to find us an LCD and get rid of all these fractions. So what's our LCD going to be this time? 4x. So just like we did yesterday, we're basically distributing that 4x through to all of these. So I'm like, okay, so on my first one, the 4's cancel. So I have an x left over that I'm multiplying by because the fraction's gone. Then I get to the next one. The x's are going to cancel. So here, I got to get my color out. I have the 18 there. If the x's cancel, I still have a 4 left. And then when I get to the end, nothing cancels. So I just have 4x. Because again, this 4x is just basically multiplying by your numerator all the way across. See, I like questions like that, even though I can hear them because I have huge ears. Hardy, why didn't you just subtract the 3/4 at the beginning? That's actually a really good idea. And if I'd have been using my brain as bigger as you were right there, I would have done that. So yes, that absolutely would work. And then you just have a proportion, and that's going to be even faster than what I'm doing. This will work, though. Minus the 3x over. Oh, those juniors are slow. And again, like we talked about yesterday where we said, hey, if they're working together, it better be faster than the days that they're just doing it on their own. Well, here it's the same thing. Together they can do it in 18. The seniors are at 24. We knew it needed to be more than 18. We wished it wasn't like 2.5 months, but hey, you know, they're working on it. They're trying to get there. And so that's how this would set up and work. So that in general, again, like we did with the jobs yesterday, is basically that's your setup each time. That's what we're trying to get used to when we're doing these charts and things, and why we need to practice to make sure. The next portion, and there's only basically about, I think there's 3 different kind of types of these. Mixture problems. You know, if I want to blend a little of this and a little of that, how much do I need of each? Something like that. Amount, price, total. Again, generic. Very generic titles on these. Whatever's going to make sense to you. But here's what I want you to know as we move forward with this. If you make these charts, the equation that you're solving is always going to end up in this last column. You're going to add, as it has here, these two together, and it's going to equal what's on the bottom. So you're not going to have to worry about what side of the equation does this go on, what goes what. If you set it up this way, it's going to do it for you every time, which is really nice. And so for every one of these that we're going to do moving ahead, I'm going to make a chart. So if you get to a point that you don't think you need a chart, hey, then don't use a chart. But I think I'm going to. So let's give one of these a go, or at least a couple. Let's play with a couple of these. All right, who we got first and what are we doing? Mia. All right, Mia. Adds a 70% acid solution to 12 milliliters of a solution that is 15% acid. Ooh, we're getting scientific. How much of the 70% acid should be added to create a solution that is 60? You're like, okay, whole lot of wordiness going on here. So we have a 70% acid solution. So, okay, I'll just put 70 in here. Added to 12 milliliters of a solution. So this should say milliliters if it's milliliters. So the 15%, I know how much I have. I have 12. Here comes the kicker. How much of the 70% acid? I don't know. That's what I need to figure out. Should be added to create a solution that is 60% acid. What I'm always trying to get to is on the bottom. So you're like, okay, so back on the last page, it said you're going to multiply these two together to get what's in the end. That's going to be our setup for these. So we got 70x plus 180 You're like, Hardy, nothing there. Okay, let's think about this for a minute. Let's say I told you, I'm going to get creative here for a minute. Let's say, what if I told you, instead of that being X, that was 8. So if I had 8 milliliters of 70 and 12 of 15, how many total milliliters would be in my beaker? 20. Okay? What if I said there were 25 milliliters up there? 37, okay? Because we're adding them, right? Oh, dear. Oh, dear. This thing never sticks to anything. Does it stick now? There we go. So how many milliliters do I have total in my beaker in this case? 12 plus X, or X plus 12, either way. Just not 12X. We're not multiplying, we're adding. And so my mixture, if I distribute that 60, gets me to here. And just like I said on that last page, there's your equation. It's set up already. So 70x plus 180 equals 60x plus 720. And now we're back into the Algebra 1 game. So let's see here. 60x over, 180 back over, divide by 10, 54. Now, these are word problems, they're applications. We need to know what the 54 is. So 54 milliliters of, 70. 70% solution. I don't even care if you just put 54 milliliters of 70%. That's fine. That tells me enough. But don't just tell me 54 milliliters. It might be like 54 milliliters of what? 54 milliliters of ketchup? 54 milliliters of what are you talking about? And then you get into that whole argument. So, but that's going to be the generic setup. Now, we're going to skip 3 because we're talking about all these juices and things again. I want something more compound here, especially middle of the morning. Let's talk about fruit and nuts. There we go. Okay. So, same setup. You can decide what you want to title all these different things. So like I'm like, okay, so we got weights here. So we got pounds. We got how much does it cost per pound? And what happens when we mix them together? There's no rhyme. You can even have no titles at the top if you wanted to be perfectly honest. But I like to get a little guidance here. All right, let's see what we got. Ziggy. Ziggy's got 4 pounds of mixed nuts that are $12.50 a pound. And he's going to make some trail mix, all right? Now, he wants to make trail mix that costs $9 a pound. I'm not putting 9 here. We're making this mix, so the 9's going down here. I'll explain how I knew that in a minute, in case you're like, how'd you know to put it there and not there? How much fruit mix, we don't know, that is $7 a pound will he need to make it? So here's another way I would know that that's true. If I'd have put the 9 here and the 7 here, if I'm mixing stuff that's $12.50 with stuff that's 9, I don't think I'm going to get stuff that's worth less, okay? That doesn't make any sense. These two together, the average will be somewhere in the middle. So that's one of the things I'm wanting to watch for with this. And so now, after the last problem, hopefully I realize if I'm dumping these nuts and this fruit mix into my big container, you'd have to add these up. And now we're just multiplying. Again, still multiplying to get the last column. And still distributing the 9 to each piece of that. There's my equation. I mean, one nice thing, if you do happen to make a mistake, and it's likely, Like, let's say you work through one of these and all of a sudden you're like, wait, I'm getting negative pounds. Okay, that doesn't make any sense. Usually that will guide you to go back and look and change something. At least I hope it would. All right, what do we got this time? 7 pounds. 7 pounds of something. 7 pounds of fruit mix. So what do we have? We got acids and fruit juices and mixed nuts and fruit. I mean, we got lots of things. But anything that's like a mixture of types, that's the route you're going to roll with these when you're trying to work through. The other type that we're going to look for, and Hardy will admit, Hardy's least favorite, but we're still going to do this, is the distance equals rate times time problems. Depending on what info you have, you might want to rearrange it when you make your equation. It's just going to depend. So, Maria and John, they're going to a business conference. Maria travels 110 miles in the same time that John travels 140. Okay, Maria went 110 for distance. John went 140. Okay. John travels 15 miles per hour faster than Maria. Okay. So, if Maria, let's kind of think this through. If Maria was going 40, how fast would John be going? 55, because we're adding 15 to it. So if Maria's going, we don't know, John's going, we don't know, plus 15. And again, you can use X for all of these if you want to. But now, find the average rate per person. So, if distance equals rate times time, so let's see here. So, if I've got these two and I don't know anything really that's going on here, I'm like, so if I got D and R, distance divided by rate equals time. So if that's true, and again, it's that last column we're always looking at. So I've got 110 over R, because I'm doing division. And I've got 140 divided by R plus 15. And there is no third thing to set them equal to, so these two are going to be equal to each other. So, 110 over R equals 140 over R plus 15. We have a proportion. Don't try to deal with something fancy here. Don't worry about some LCD or something like that. We're just going to cross multiply and work this through. Make sure you distribute that 110 to both of the terms. And the nice thing with these as well is going to be when you get to an answer, you're going to be like, all right, does this seem reasonable? Well, so let's see here. So 55 miles per hour. So Maria was going 55. And Johnny here was going 70. So either John was a lead foot or Maria was like 90-year-old grandma going down the road. So we're not sure which. So that's going to be our thing here. You're always going to have that chart that gets you all the numbers. You can figure out where to put things. But based on what you know or can figure out from the equation, that's how you're going to have to manipulate it. Sometimes you're going to have distance and rate. You're going to have rate and time. You're going to be able to find distance. Sometimes you're going to have distance and rate. You're going to need to manipulate to find the time. It's going to depend. I know that drives some of you crazy because your mathematical brain is telling you, okay, there's got to be one direct way to do this, Hardy. No, there doesn't. So, unfortunately, that's what we kind of are looking at with these. Let me throw one last twist at you. One last, because I'm going to show you an easy one once we do this. Last ones, 7 and 8. And again, if you ever want to go back and mess with the others, I've got all of them posted. I just don't want to put you through like 35 minutes of crazy. Okay, we got Xena. Xena's rowing on a canoe in the lake, hopefully. Her rate in still water is 6 miles per hour. It took her 3 hours to travel 10 miles round trip. Assuming she kept at a constant rate of speed, determine the rate of the current. Oh my gosh, okay. Distance, rate, time. I'm going to add one piece this time. So when she's rowing, it mentions here the rate in still water, and it talks about the current. So whenever you're in water, at some point you're going to deal with a current, whether you're going up or downstream. So I'm going to kind of label this upstream and downstream. When you're going upstream, you're going against the current. The current's against you. When you're going downstream, it's wee! You get to just kind of float along here. So, what do we know? Well, let's see here. What do we know? Xena's rowing on a canoe. Okay. Distance. She's going 10 miles round trip. So she started, she went somewhere, she came back to the same spot. So my distance isn't 10. I went 5 miles one direction, turned around, came 5 miles back. There's my 10. Oofda, we're already having to think about stuff like that. Her rate, okay. Her rate in still water is 6 miles per hour. Okay. Both of these get a 6, but there's going to be some sort of current in the water. When you're going upstream, it's going against you, so it's going to slow you down. So whatever that current is, it's slowing me down when I go upstream, but it's helping me go faster when I'm going downstream. You're like, how am I supposed to just know this stuff? I know, it's kind of tricky because I'm not a canoeer, but, you know, we got what we get. But we do get one more piece of info. It takes Xena 3 hours to travel all this. So you're like, oh, so we're just going to, this is going to be 3. No. You're like, dang it. So just like before, these are the 2 things I've been able to get pieces of out of here. We're not forgetting the 3. So if we go like we did on the last one, the distance divided by rate is going to be time. Here's the thing. So when you're canoeing, I'm going to put this into words to make it go a little bit better. At least I'm hoping that's going to work here. When you go upstream, and then you turn around and you go downstream, that's going to equal your total trip. Okay, so what does that mean? That means that my upstream equation, oops, I can't believe nobody yelled at me about that, plus your downstream equation equals your t. How long did I travel? I traveled 3 hours. This time, we gotta play with an LCD. But it's not going to be a bad one. Because again, the 3 is your numerator. Do not think this is part of your denominator. It is not. 6 minus c. 6 plus c. Okay, the 5 is there. The 6 minus c's cancel. So we're left with a 6 plus c. When I get to my middle fraction, the 6 plus c's cancel. I am left with a 6 minus c. And then here on the end, I'm going to do my multiplying ahead of time. If I multiply this out, so let's see, I got 36 plus 6c and minus 6c are going to cancel. So we don't have a middle term. That's at least nice, but they're like, oh, Hardy, there's c squared. Ugh. This is going to get really good, so just kind of stick with. When I distribute all this stuff out on the left, at first, naturally we would think, okay, everything's got to get to the c squared side. But hang on a second. When I simplify the left, so 30 and 30 is 60, okay. Ooh, plus 5c and minus 5c, they cancel. Yes! I get to do a regular algebra equation. I'm not going to have to do no fancy factoring. Minus my 108 over. No worries about the negative in front of my c squared. It's about to go away. Divide by negative 3. And now we got to use a little common sense. Yes, I know mathematically there are two answers, positive and negative 4. But I don't think the current can be negative. That would be weird. The current is 4 miles per hour. So going upstream, we're going to go really slow. We're only going 2. Going downstream, we're going really fast. We're breezing at 10 miles an hour. So you're like, Hardy, getting tired of all these being like this. This is like brutal. Last one to show you that some of these can be simple. And then we got everything covered. And you're going to have 2 days full in here of just doing stuff and not listening to me yibber for half an hour. So, last one. All right, let's keep one simple. Deshaun, he drove to his uncle's house in 5 hours. When he returned home, there was less traffic, and it only took 3 hours. If Deshaun drove 26 miles per hour faster on the return trip, how fast did he drive each way? Okay, so let's see. He was going to his uncle's house, and then back home. Okay. Let's see here. Deshaun drove there in 5 hours. So to me, that sounds like time. So 5 hours to get there. When he returned home, there was less traffic. It only took 3. Okay, back home only took 3. If Deshaun drove 26 miles per hour faster on the return trip, he was driving 26 miles per hour faster. How fast did he drive each way? Okay, so here's where my info is this time. So distance equals rate times time. I'm not having to manipulate anything. I'm not having to solve for a different variable. That's just what the variable is. So if that's true, rate times time, 5r. Rate times time, 3r plus 78. He went the same distance. He went from home to his uncle's and his uncle's to home. The distance has to be the same or equal. So, yeah. So let's see. So 2 uncles, we went 39. Oof, duh. And back home, 39 plus 26. Okay. And we're off and running. So, here I go, boy. I'll repeat what I said before, kind of on how we're going to break this down a bit. And what I did to try and assist you in working through it, not driving yourself insane. So, on this 5 through 8, where these are all spread out, there's charts, there's things to kind of help you get thinking about it as you're going through. When you're working your way through these, okay, if you are going even, because again, even on the key that I put online, the odds you have answers, the evens you have work shown. So if you want to check with that, you can. Copying it, probably not a good idea, because that's going to drop a hammer on you on the test. But if you go the evens route, okay, for your own sake and safety, skip the SpongeBob problem. Skip 16. Because an extra twist got thrown in on that. And I'm serious, I even sat and was working it and staring at it and working at it. It was driving me nuts. I will not put something crazy for you on the, I should say the second SpongeBob problem, number 16. SpongeBob's also at number 15. So just kind of keep playing, keep manipulating. If you have to peek at something with an answer every once in a while, you can and work it back. But do make sure at some point you're working start to finish on trying to set some of these up. This is one of those things you have to get on the struggle bus and work through. Because I could tell you how to set up every single one, but if I do, you're going to get to the test and it's going to be a big old blank. Big old blank canvas here, which we don't want to